Hello everyone, welcome back to my YouTube channel. Today we are going to discuss stability of a system. So a system being stable typically means that all the roots of the characteristic equation representing that particular system will lie on the left half of the S-plane. We have said it multiple times before, that is all the poles will lie on left half of S plane. This is S, this is j omega, this is the S plane. So all the poles will lie on the left half of the S plane. That is the criteria for stability. So I'm gonna write some location of poles on S plane that determine whether a system or stable or not. I'm gonna give you some general equations and whether they are stable or not. So first of all, I'm gonna I'm gonna give a heading that is location of poles on S plane for stability. Location of poles on S plane for stability. So at first I'm gonna give you an equation that is a Laplace equation, that is m of s is equal to a by s plus a. Here on taking Laplace inverse, okay, before that we'll find the pole of this equation, pole of this system, particular system with the equation m of s equal to a by s plus a. The pole will be s plus a equal to 0 and s equal to minus a. The pole will be, how will you find the pole? You'll equate the denominator with 0 to 0, I would say. So in the S plane we'll get minus a. This is how you get the pole of that given system. Next, what I'm going to do is I'm going to show you how this graph originally looks, how this particular equation forms a graph. For that I'm going to write the Laplace inverse of the given equation. That will be, the equation is 1 by s plus a, so obviously its Laplace inverse of 1 by s plus a will be what? It will be e raised to minus at. This you have studied in your engineering mathematics class, so I'm not saying it again, I'm just showing you the equation. So it will be e raised to minus 80. Now that we have an a here, so it will be a e raised to minus 80, and the graph of this particular equation is, it's an exponentially decreasing function. It's an exponentially decreasing function. So this is the graph of a e raised to 80. Okay, that from this graph we could say that it is exponentially decreasing as time increases. As time increases, the graph itself is decreasing. So it is like tending to kind of like 0 or some small value rather than going to infinity. So we could say that the system is stable. That is the main factor to represent a system as stable is that the pole should be on the left half of the S-plane. But if you know how to draw the graph of the given equation, a given system, if you know how to draw the way to draw the graph of the system, then you could also say it from the graph itself. So either this way or this way you can say. I'm just writing this way for like better understanding of the subject. Now we'll move on to our next equation. We have done s plus a, so we'll do s minus a. What will that be? A by s minus a. The pole will be s minus a equal to 0, s equal to a. S equal to a. So how will s equal to a look in S plane? It will be on the right half of the S plane, right? It's on the right half. So we could say it is unstable. We can also draw this particular functions actual graph, that is m of t, that will give a e raised to at. Is actually what that will look like. So when I draw that particular graph, it will be an exponentially increasing function. Exponentially increasing function, not a decreasing function. That is, as time goes on, as time increases, the graph is tending to infinity. It basically means that the graph is going to be unstable. It's going to get higher values as the time goes on. It's not stable. So this is the base for stability. That is, if a graph is unstable, the pole will be on the right half of the S-plane. So this is the basic equations that we have discussed. We will move on to some other equations as well. So I am moving to next equation, that is m of s is equal to a by s plus a plus jb plus a conjugate by s plus a minus jb. Okay, on drawing this graph, on drawing this particular graph, that is the m of t graph, the m of t graph of this particular equation will look like something like this. That is, it's a sine wave which is decreasing with the time. A sine wave whose amplitude decreases with time. That's what we will get as the m of t of this given particular equation m of s. And from the equation m of s, we could find out its poles. Its poles will be basically s equal to minus a minus jb and s equal to minus a plus jb. Right, if I equate this value to 0 and this value to 0, I'll get two values of s, and these are just two values. Okay, so on plotting these two on a graph on the s plane, I would get minus a will be somewhat like the here, and the value j beta, that is minus a plus j beta, will be here, and minus a plus minus j beta will be here. So we could say that both the poles of the given equation lies on the left half of the s plane, hence the system is stable. Or from this diagram we could say that the amplitude is decreasing towards 0, that is like converging to a smaller value, hence we could say the system is stable. And we'll move on to our next equation, which is similar to the one we have written above, that is m of s is equal to a by s minus a plus jb plus a conjugate by s minus a minus jb. Okay, so this graph will be just the opposite of the one above. It will be just the opposite, as I could say. It will be an increasing function, that is, its amplitude increases with the time. So I could write it like this, that is, its value is increasing with respect to time. And on drawing the poles, it will be s equal to a minus jb and s equal to a plus jb. On plotting these two in the s plane, we could say s j omega. We can see that a is on the right half of s plane, or I could say positive s plane. So here a is here somewhere, and then a plus jb will be here, and a minus jb will be here. So we could say here the roots lie on the right half of s plane, and hence we could also say that the system is unstable. Then we'll move on to our next equation, which is of the form m of s equal to a by s plus jb plus a conjugate by s minus jb. Okay, the graph of this equation is particularly different. Actually similar to the both two. It's also a sine wave. It's also a sine wave, but it will differ in some ways. That is, if I'm drawing it, it will look somewhat like this. That is, it is stable. Okay, Then if I consider the roots and draw them in the s plus j omega x s plane, it will look like, that is, the roots will be s minus jb and plus jb. So it will be like here and here, jb minus jb. And these two poles lie on the j omega axis, which is different from what we have seen before. So how will we determine whether it's stable or not? Here we can say that the poles are simple poles, that is, jb is only once and minus jb is only once in the imaginary axis. So we could say that this given system is marginally stable. Marginally stable. Okay, it is marginally stable. But there is another condition possible, that is, I am considering the next possible equation, that will be, okay, that will be a sixth equation, that is m of s equal to a by s plus jb the whole square plus a conjugate by s plus s minus s minus jb the whole square. Okay, on solving this given equation, you will get s equal to jb comma jb and s equal to minus jb comma minus jb. Minus jb is the root of the first equation and this one is the root of the second equation. So on solving these two, we got answers, that is jb and minus jb, plus jb and minus jb. On plotting this, we could say, on plotting these, it will be the same poles only, no? So there will be 2 plus jb's and there will be 2 minus jb, that is, it has double poles. This given particular equation has double poles. So we cannot say the system is marginally stable. Instead, we will say the system is unstable. The system is unstable. And its graph will be somewhat looking like something something increasing in its amplitude. So that's why we say it is unstable. If it was marginally stable, there will only be single pole. Here it was double pole. The single pole will make the system marginally stable. Single pole on the imaginary axis will make the system marginally stable. If there is double pole or multiple poles on the j omega axis, then it will be an unstable system. So now we have seen 6 basic formulas and the location of poles on each and every one of them. So I hope you all understood what we have discussed today. In the next video, I'm gonna continue the topic, that is stability, and I'm gonna show you how to do problems on Routh-Hurwitz criterion. I'll be doing 2-3 problems and including some variety of conditions in that problems. So please stay tuned, and also if you like this video, please like and subscribe to my channel, and thank you so much for watching. Have a nice day.